Welcome to EpiJournal, a collection of notes and insights into the field of epidemiology. Part 2A, Measures of Effect. This is covering risks, odds and rates ratios. So in the previous session we went over risks, odds and rates. For this we're going to be going over ratios. And remember, this is part A, so we've got some more measures of effects in part B. Right then, so let's start off with some housekeeping, and then we'll go into each of them in turn with examples and issues that I've come across in my understanding that I hope will be able to go and clear things up on your end. So let's start with housekeeping. Magnitude of effect, exposed versus unexposed. Exposed with outcome divided by not exposed with the outcome. So risk, rates, and odds. You can use ratios for each of them as suggested at the beginning. It is essentially saying by how much does being exposed matter. And as a little disclaimer, I want to note that if the disease is rare, then the risk, rate, and odds ratios will be similar numerically. Just to keep that in mind. But they do mean very different things in their interpretation, and sometimes the interpretation is not followed in the literature, and it is a bit of a frustration on the reader's end because you don't quite know what they're talking about some of the time, unless you're looking at their calculations specifically or you look into their methodology. Anyway, let's start off with what is on top of your calculation. So let's say you want to compare drug A to drug B, and we are talking about survival between treatments with drug A versus drug B. Now, in this case, because survival is the outcome that we are measuring, the higher numbers in this particular calculation will be in drug A's favour, because they will. However, if you change that round to mortality, then higher numbers will not be in drug A's favour. So be clear in your head what the outcome you are measuring what the outcome is, and just make sure you're very, very particular on these things, because you can sometimes going to get muddled up. Right then, let's go on to risk ratios. Now, risk ratios, R1 over R0. R1 is exposed versus non-exposed. Then I'm going to go into risk differences, or relative risk in percentages, percent increase or percent decrease. This point 2 here, risk differences, will be able to be used in odds ratios and rate ratios also. So be very, very clear on this second point. And the third point, I'm going to go over some issues and confusions that I personally had with other calculations that you may find or you're taught, and just to go and clear the air there. Right. Risk ratio, risk in exposed versus risk in unexposed. So let's say we have two areas, and this is we've got cholera, okay, in these particular areas, and we got exposed area, which we think is exposed, or the area we're testing, versus another area which we're going to be using as the unexposed. Okay, so what do you do? Risk in the exposed versus risk in unexposed. From what you learned in the last session, you're going to be using your count of new cases specifically, because this makes it a risk, not a prevalence. Risk per one person, you do your calculation, 489 divided by 4656, you're going to get that, then you're going to get that. Then you chuck those numbers in the risk ratios, or you can go and make it risk per 100 if you like, chuck them into there, there's your risk. It doesn't matter if you are putting the risk per 100 or risk per 1 or 1,000 or a million, it's still going to come up with the same risk ratio. Risk ratio in this case is 2.62. Now, do you have a 2.6 times more risk of contracting cholera in A opposed to area B? No. is a simple answer to that. That is an incorrect analogy to be using. Now, let me explain. I'm going to go, this is the second point, which is you can be using in all of these other ratios, and it's relative risk. Now, if the risk ratio is 1 or close to 1, it suggests very little difference between the two. If it's above 1, it suggests an increased risk. If it's less than 1, then it suggests a reduced risk. So that's pretty simple, okay? So, the correct definition of this would be Area A had a risk of 2.6 of getting the outcome of cholera related to Area B. Or, the risk of getting cholera in Area A was increased by 160% compared to Area B. Now, you'll note that in Area A, I'm not saying increased or decreased. Sometimes when you're trying to write these things out, it's easier to go and say increased or decreased just because of the sentence structure. It's saying you just had a risk of 2.6 of getting the outcome of cholera relative to the other area. It doesn't roll off the tongue very well. So people always want to go and chuck in more or less, but practically chuck it into a percentage. That will that allows you to go and say increased or decreased, just as a rule that I'm trying to follow myself. So yeah. Now I'm going to go give some examples of risk where, let's say, equals 1. I'm just going to make it absolutely clear for you listening at home. So it's close to 1. It does not show much evidence of any protective effect or anything. All right. So risk of cancer in non-smokers is 14% versus risk of cancer of smokers is 15%. Okay. So we can go and have a risk ratio of 15 divided by, well, 14 and 15 would be like 0.14 or 0.15. So 15, which is the risky thing that you're thinking that you're trying to measure, which is cancer, which would be the 15. 15 divided by 14, 0.07. So that shows smoking shows a risk of 1.07 of having cancer compared with the non-smoking group. That's very, very close to 1. That doesn't really, in a lot of case controls, and if you're a case control, then it's about times 3 perhaps would show a good significance. Cohort studies, I think it's 4 you want to be kind of aiming for to go and show that, oh, there's definitely something going on there, but this is, you wouldn't be very happy with this. Right, so let's say if it's far greater than 1. We've got this thing, we've got cancer, smokers 22, so 22 divided by 14, that equals 1.6. Show smoking shows a 1.6 times the risk of having cancer compared with the non-smoking group. Or, now this is important, just note this, a 60% increase in risk of having cancer as a smoker compared with the non-smoking group. That makes, that kind of flows across the tongue a little bit nicer, in my opinion anyway. And you can probably go and guess how I've calculated that. But I'll carry on going on. So we got we're going to go the other way. So cancer seems to be protective, 0.6. So those who don't, we're going to flip it round, and we're going to say we're going to show the protective effect of non-smoking instead of saying the increased risk of having. So you've got an increase of risk of having cancer if you're a smoker. We're going to go and have a look at what the protective effect of being a non-smoker is, and that 0.6, which is not 60%, as you'll note. It is you are 40% less at risk of cancer if you belong to the non-smoking group in this study. Make sure you go and you're covering all of your bases here. And you can probably infer how I'm calculating this also. Right then, so relative effect. I'm just going to go over this as plainly as possible in case you haven't figured it out. relative risk -1. If it's greater than 1, then you want RR -1 in brackets times by 100. If it's less than 1, it's for a percentage decrease, it's in brackets 1 divided by the risk ratio, close brackets, times 100. Right then, so this should be pretty simple. Now we're going to go and we're going to chuck in cancer of non-smokers versus cancer of smokers in this situation. And as you can go and see, we've got the numerator and denominator swapped in both of these. Now, in this, you've got the smoking group on the top, for how much of an increased risk are you of cancer if you are a smoker, and we're going to also want to go and find out how much less at risk of cancer are you if you're a non-smoker. Okay? Because less and more is just easier to say, and so you've got this kind of a risk compared with this other group. It means that you can go and say, is this more or less? It's just easier just saying it even. Anyway, so you got 1.57 and 0.63. Chuck that into the calculation there. We've got a 57% increase at risk of being a smoker and 37 less at risk. There you go. Hopefully that's simple for you. It's surprisingly took me a while to go and kind of make sure I get it through into my head, but that is because things are going to get confusing later on when you talk about particular studies. Now, this website is fantastic, and I would highly recommend going onto it because it just explains it in quite a clear fashion. But to be precise, it's not correct to say that smokers had 1.57 times more risk of having cancer. That's wrong. If you want to add the more or less, you just turn it into a percentage. Just keep that as a rule of thumb. Okay. Now, issues and confusions, as I was talking about beforehand. Have you ever seen this? Whenever you're being taught some things in this kind of thing, you have these analogies of A divided by A plus B and all this other rubbish, right? Now, how does that relate to this table that we got here? This is more likely a table that's you actually go and get in actual raw data itself. So where does this is just this calculation above is just adding to confusion right there, and that is because it is talking about a study design, specifically case control or cohort. Now, what it's talking about is where you have I call it a test, just a test table, where you have from this, if it goes ahead, you've got your exposed and non-exposed versus the outcome versus non-outcome. That's where the A, B, C, and D comes from. So again, how do we go and calculate this with a normal table of normal data? Now, in simple terms, the cholera cases would just be the outcome, right? Exposed versus unexposed. That's easy to go and put in. Not outcome, well, also simple when you think about it. It's just you just take away the numbers, and you go and get these numbers. So once you go and add all of that in, and we go and actually put all the calculations in, and we do an equal sign, click enter, we go and get 2.62, right? So that's a 162% increase in risk of having cholera in A compared with area B. Now, you'll note that this is exactly the same as just doing it the other way. So just note that, because this completely threw me, when looking back at my previous notes, I was like, what is that? No, it should be simple. It's a ratio. What's going on? No. So just keep that in mind. Whenever you go and see these other calculations for the same thing that you're trying to calculate, they're all interchangeable and they all produce the same thing. Okay? Right then, hopefully that helped. Now let's go on to odds ratios. Okay. Derived from case controls, we're talking about rare outcomes normally. Again, if it's greater than 1, it's, yeah. Just want to note that odds and odds ratios are not proportions. An odds ratios of cholera in area A is 0.5. This means it has 0.5 times the odds of getting cholera in area A compared with area B. Just note that, not more, not less, just it has this times the odds. Just state that. Right then, odds with the outcome with exposure, odds with that in outcome without exposure. That's how to look at it. It's not just in exposed group versus non-exposed group. This goes with all of them. You're talking about the if they've had the outcome, the odds of the outcome with versus without. Okay? How many times more likely are the odds of finding an exposure in someone with the outcome compared to finding the exposure in someone without the outcome? Sometimes just getting it really, really precise in your terminology can kind of make you think twice about it. Now, again, we've got equal odds, increased odds, or decreased odds. I covered that in the previous one. So now we've got exposure versus the outcome. Exposed and non-exposed versus symptomatic and non-symptomatic. Okay? In this case, we can use these A, B, C's, and D's. And there are lots of ways to do this. Now, the first one is patients who are symptomatic have an odds of X of being in the group who are exposed. Patients who are symptomatic. That is this, divided by this, divided by this, divided by this. Should be simple. I like this method better. Patients who are exposed have an odds of X of being in the group who are symptomatic. I like it starts off with the exposure. It just works in my mind a little bit better, and that's that divided by that, divided by that, divided by that. Now you can also do it this way, and that is this times this divided by this times this. I mean, they all produce exactly the same thing. Just pick one, and there you'll have it. So I've picked this one. That's my favourite one of way of thinking about it. And we've got an outcome of 2.63. Okay? Patients who are symptomatic have an odds of 2.63 of being in the group who are exposed. Okay? If we do it this way, which is my favourite way, patients who are exposed have an odds of this 2.63 of being in the group who are symptomatic. Same thing. Gives exactly the same results. Just pick your favourite one and stick with it. Alright? Now, what about in a different format? Remember beforehand, this is for a test table, as I've dubbed it. Now, let's say we want to go and turn it into like a normal table that you just have your total data and etc. So you just add them together, you're going to get your total people, then you can do your risk there, and then you can do it because if you're able to do an odds, then you're going to be able to do a risk. Okay? Or if you do able to do a risk, then you're going to be able to do an odds. However, not the rate, because rate is just a different beast altogether. However, a rate can do, if you know you can do a rate, because it's time at risk, I guess. It's very, very confusing with all these risks and rates flying around interchangeably, but it's using a time of exposure per person. So, yeah, but if you can do that, if you've got a rate, then you can produce the risk, odds, and rates. Now, risk, you can always go with odds, just to state that. So we've got, in this case, we've got both. How fantastic. Now, risks and odds derived from case control and cohort. Rate you can only go get it from cohort. Just stating that. Now let's go and calculate the risk ratio and odds ratio. How wonderful! And you have so many calculations that you have access to, because you picked your favorite one, but you can use 3 of them. This for the odds ratio. Okay, so risk ratio, we've just got this divided by this, 2.18, or you got a risk of being exposed. So being exposed gives you 118% increase in risk of being symptomatic. Can't make sense, right? That and that. Odds ratio, do exactly the same thing. 2.63. Remember, 2.18, they're similar numerically, just to state that. So we've got that divided by that, produces 2.63, 163 increase in odds of being symptomatic. Okay, so remember, state the odds as an odds, not as an increase or decrease, and if you want to increase, make the increase or decrease, make it a percent. Just remember that, please. Please, oh God. Right then, rate ratios. Let's go into rate ratios. Okay, so for this I've got a particular example. We've got an investigation of exposed versus unexposed. For example, we have 2 mining companies. We want to see if they're skimping out on the PPE, right? Personal protective equipment, by comparing against a gold standard company. So we've got 3 companies overall that we're looking at. So we recruit individuals from each and we follow them up over time, and specifically we're looking at lung cancer. Right then, here's our result. We got total person years for each of them, and we got new diagnosed lung cancer. Cool. Got our rates per 1 person year, rates per 100 person year. Okay, how fantastic. So what we're going to do with this, R1 divided by R0. R1 total is the population of interest, where we predict the change versus the population we're comparing against. Alright, so it could be drank the predicted bad water, live near Chernobyl, because I just watched that series and it's awesome. Or maybe vaccinated, perhaps. Or the opposite and not vaccinated. But actually, vaccinated is a whole different thing, and I'm going to go over that in part 2b. So we got our R0 thing we're comparing against versus R1 and R2, which is just the 2 things that we're going to use as the numerator. Okay, so here we go. 0.87, which is company A, versus the gold standard, which is 0.31, gives you that. Then we've got R2 divided by R0, which is that, and that. So, what do we get? Company A employees have 2.8 times the rate of getting lung cancer as compared with the gold standard. So that's an 181% increased rate of new diagnosed lung cancer compared with the gold standard. However, Company B employees have 0.25 times the rate of getting lung cancer compared with the gold standard, or a 48% rate reduction in the new diagnosed lung cancer as compared with the gold standard. So it's just that Company B is doing something pretty good that the gold standard company could actually learn a thing or 2 from. Oh, right. I hope that has helped. It has certainly helped me discussing all of it. And yeah, I will go see you in the next one. Over and out.